We're told the Big Bang was the beginning of everything. Time, space, matter, energy, the laws of physics themselves, all of it burst into existence 13.8 billion years ago, in an inconceivably hot, dense point that expanded into the cosmos we see today. It's presented as the ultimate origin story, the moment when literally everything began. Except, what if it wasn't? What if the Big Bang was just another Tuesday in the life of a much older, much stranger cosmos? What if we're living in universe number 10 to the power of 500, completely unaware that this exact scenario, this exact moment, has played out countless times before? What if the Big Bang wasn't the beginning at all, but simply the latest reboot in an infinite series of cosmic do-overs? For all our confidence about the Big Bang, for all the evidence supporting it, the cosmic microwave background radiation, the abundance of light elements, the expansion of space itself, there's a dirty little secret that physicists don't often advertise to the public. We have absolutely no idea what caused the Big Bang. None. Zero. We don't know what came before it, assuming the word before even makes sense in this context, which it might not. When you run the equations backward in time, everything breaks down at T(s) equals 0. The temperature becomes infinite. Density becomes infinite. The curvature of space-time becomes infinite. Our physics, all of our carefully tested theories, literally cannot describe the moment of creation itself. General relativity gives up. Quantum mechanics throws up its hands. The math produces infinities and nonsense, which is the universe's way of telling us we're asking a question our theories can't answer. This isn't just a temporary gap in our knowledge, something we'll figure out once we get a bigger particle accelerator or a better telescope. This is a fundamental wall. At the Planck time, about 10 to the negative 43 seconds after the supposed beginning, our understanding of physics completely evaporates. Before that moment, and I'm using before very loosely here, we're in territory where quantum effects dominate space-time itself, where the smooth fabric of reality becomes a chaotic foam of possibilities, where time might not even flow in a linear direction. We call the Big Bang the beginning because it's the earliest state we can meaningfully describe with our current physics, but that's very different from saying it was actually the beginning of existence. Think about it this way. Imagine you start watching a movie, but you walk into the theater 20 minutes late. The first thing you see is the main character running through a burning building. As far as you can tell, that's where the story begins. That's your frame of reference. But obviously, there was an entire first act you missed. There were events, character development, plot points that led to that burning building scene. Just because you didn't see them doesn't mean they didn't happen. The Big Bang might be like that. It's the earliest chapter we can observe, but earliest observable state is fundamentally different from beginning of existence. Just because we can't see past the Big Bang doesn't mean nothing was there. It means our instruments, our theories, our entire framework for understanding reality hits a wall at that point. So, if the Big Bang wasn't necessarily the beginning, what was it? One possibility, proposed by multiple physicists over the past century, is that the universe undergoes endless cycles of expansion and contraction. The Big Bang, expansion, stars and galaxies forming. Eventually, the expansion slows, reverses, everything collapses back into a big crunch, which somehow triggers another Big Bang, and the whole process starts over. Rinse and repeat. Forever. No ultimate beginning, no final ending, just an eternal cosmic heartbeat. Expansion, contraction, expansion, contraction, on through infinite time. Our Big Bang was just the most recent bounce, the latest iteration, and there will be another one after our universe eventually comes to an end. We're not living in the universe. We're living in a universe, one of an infinite series stretching backward and forward through eternity. Now, you might be thinking this sounds like some fringe speculation, some wild idea cooked up by a sci-fi writer who had one too many. But actually, the cyclic universe hypothesis has been proposed by some of the most respected minds in physics. Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work on black holes, has developed something called conformal cyclic cosmology. Paul Steinhardt, a theoretical physicist at Princeton, has proposed the ekpyrotic universe model. And actually, the idea of an oscillating universe goes all the way back to the 1920s and 1930s, when cosmologists first started grappling with Einstein's equations and what they implied about the universe's fate. These aren't fringe theories proposed by crackpots. They're serious attempts by serious physicists to solve real, substantial problems with standard Big Bang cosmology. Problems that don't have better explanations. So, what are these problems? Why would anyone even consider something as weird as an infinitely cycling universe? Well, let's start with what's called the past hypothesis or the low entropy problem. When the Big Bang happened, the universe was in an extraordinarily low entropy state. Now, entropy is essentially a measure of disorder, of how spread out and randomized energy is in a system. The second law of thermodynamics tells us that entropy always increases over time. Things go from ordered to disordered. A glass falls and shatters. Heat spreads out. Stars burn out. The universe moves toward maximum entropy, toward heat death, where everything is the same temperature and nothing interesting can ever happen again. But here's the thing. If entropy always increases, if the universe is always moving toward more disorder, then working backward in time means the universe must have started in a state of incredibly low entropy, of incredibly high order. And it did. The Big Bang was extremely smooth, extremely uniform, with only tiny density fluctuations that would later grow into galaxies. But why? Why did the universe start in such an unlikely low entropy configuration? If you were to randomly select a configuration of matter and energy from all possible configurations, you'd overwhelmingly get something that looks like heat death, not something that looks like the early universe. The odds of randomly getting a low entropy beginning like the Big Bang are so astronomically small that calling it unlikely doesn't even begin to capture it. It's like shuffling a deck of cards and having them come out in perfect order. Possible, technically, but so unlikely you'd never expect to see it happen. Standard Big Bang cosmology doesn't really explain this. It just says, well, the universe started that way, and we don't know why. Initial conditions, we call them. Just accept it. But that's deeply unsatisfying, almost philosophically troubling. It's like having a murder mystery where the detective says, the victim was killed, and we're not going to investigate why. A cyclic universe, though, potentially solves this. If the universe goes through endless cycles, entropy might reset with each bounce. Or, more interestingly, the specific conditions of one cycle might naturally lead to the low entropy state of the next. The ending of one universe becomes the beginning of the next. Not randomly, but as an inevitable consequence of the cycle itself. Then there's the fine-tuning problem. The physical constants of our universe, things like the strength of gravity, the mass of the electron, the cosmological constant, appear to be exquisitely fine-tuned for the existence of complex structures like stars, planets, and life. Change any of these constants by even a tiny amount, and the universe becomes sterile. Make gravity slightly stronger, and stars burn out too quickly for life to evolve. Make it slightly weaker, and stars never form at all. Make the cosmological constant a bit larger, and the universe expands too fast for galaxies to form. The values seem almost suspiciously perfect, like someone dialed them in specifically to allow for our existence. Now, there are various explanations for this. The anthropic principle says, of course the universe appears fine-tuned, because if it weren't, we wouldn't be here to observe it. We necessarily find ourselves in a universe capable of producing observers. The multiverse hypothesis suggests there are countless universes with different constants, and we just happen to be in one of the rare life-friendly ones. But a cyclic universe offers another possibility. If physical constants vary slightly from cycle to cycle, and universes that produce complexity are more likely to survive or spawn successful next cycles, then over infinite iterations, you'd naturally end up with universes that have the right conditions for stars and galaxies and life. It's not luck. It's not divine design. It's the inevitable result of cosmic trial and error over an infinite number of attempts. There's also the flatness problem. The universe appears to be spatially flat, meaning parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees on cosmic scales. But a flat universe is incredibly unstable in the early moments after the Big Bang. Any tiny deviation from perfect flatness would have been amplified exponentially. If the universe had started even slightly curved, it should have either collapsed back on itself almost immediately, or expanded so fast that no structures could form. For the universe to be as flat as we observe it today, the initial curvature had to be tuned to an absurd degree of precision, something like 1 part in 10 to the 60th. That's not just unlikely, it's almost incomprehensibly fine-tuned. The standard explanation involves cosmic inflation, a period of exponential expansion in the first fraction of a second that smoothed everything out. But inflation itself requires specific initial conditions, so you're just pushing the problem back one step. A cyclic model, though, makes flatness an inevitable outcome. Each cycle would naturally drive the universe toward flatness, making it not a lucky accident but a predictable result. Beyond solving specific physics problems, the cyclic universe has a certain philosophical appeal, especially when you think about causality. Every effect we've ever observed has a cause. Push a ball, it rolls. Heat water, it boils. Gravity pulls, orbits form. Cause and effect is the bedrock of how we understand reality. But standard Big Bang cosmology asks us to accept that the universe itself, the ultimate effect, had no cause. It just appeared, uncaused, spontaneously, from nothing, or from quantum fluctuations, or from some pre-existing state we can't describe or understand. This violates every intuition we have about how reality works. It's philosophically disturbing, almost offensive to our sense of reason. How can the universe just begin without a cause? Religious thinkers have long pointed to this as evidence for a creator, a first cause, God. Philosophical arguments like the cosmological argument and the Kalam argument rest on this very foundation. Everything that begins to exist has a cause. The universe began to exist. Therefore, the universe has a cause. But a cyclic universe sidesteps this entire debate. There is no first beginning. Each cycle is caused by the collapse of the previous one. The chain of causality extends infinitely into the past. You never run into an uncaused first cause because there is no first. It's causes all the way down, an infinite regress that doesn't terminate. Some philosophers consider infinite regress a problem in itself, but honestly, it's far less troubling than spontaneous creation, from nothing. But, and this is a huge but, there's a massive, glaring problem with the idea of an infinitely cycling universe, and it's called the second law of thermodynamics. Entropy always increases. In any closed system, disorder always grows over time. You can create local pockets of order, sure. Life does it. Stars do it. But they do so by increasing entropy elsewhere. The total entropy of a closed system, and the universe is by definition the ultimate closed system, must always increase or stay the same. It can never decrease. This is one of the most ironclad laws in all of physics. Not a suggestion, not a guideline, a law. So, here's the problem. If the universe has been cycling forever, through an infinite number of previous iterations, each one increasing entropy, then by now we should be at maximum entropy. We should be in heat death. A uniform, featureless void where nothing happens and nothing can happen because there are no energy gradients left to drive any processes. No stars, no galaxies, no structure of any kind. Just a cold, dark, perfectly uniform sea of particles and radiation spread infinitely thin. But we're not. We're in a universe full of stars and galaxies and planets and life. We're in a low entropy state with enormous complexity and structure. How is this possible if the universe has been cycling forever? This is sometimes called the entropy problem or the thermodynamic objection to cyclic cosmology, and it's a serious one. If entropy always increases and cycles have been happening forever, the universe should have reached maximum entropy an infinite amount of time ago. The fact that we exist in a low entropy state seems to prove that either the universe hasn't been cycling forever, or something very strange is happening with entropy during the bounce. Some mechanism must reset or remove entropy between cycles. But what mechanism? How? This violates the second law unless there's some exotic physics we don't understand yet, something that happens during the big crunch or the bounce that allows entropy to be expelled or reset. Roger Penrose's conformal cyclic cosmology attempts to address this by arguing that at the end of a cycle, when all matter has decayed into photons and the universe is expanding forever into a cold, dark state, entropy becomes meaningless because there are no observers or clocks to measure it. In his model, the infinite future of one universe is mathematically equivalent to the Big Bang of the next. Time becomes infinite, but then resets in a conformal sense. It's incredibly abstract and difficult to wrap your head around, and frankly, many physicists are skeptical. But it's an attempt to solve the entropy problem. Paul Steinhardt's ekpyrotic model proposes that our universe and a parallel universe exist on separate branes, and when they collide, it triggers a Big Bang-like event. The collision might allow entropy to be exchanged or redistributed in ways that avoid the thermodynamic problem. But here's the thing. We don't know if these solutions work. We don't know if entropy can be reset. We don't fully understand what happens at the moment of a bounce, assuming a bounce is even possible. The math of a collapsing universe suggests it should collapse into a singularity, a point of infinite density where physics breaks down completely. How it avoids that singularity and bounces back into a new expansion is unclear. It requires physics beyond general relativity, probably quantum gravity, and we don't have a working theory of quantum gravity yet. String theory, loop quantum gravity, these are still speculative frameworks. So we're left with a central mystery. The cyclic universe elegantly solves multiple problems with the standard Big Bang model. It explains low entropy, fine-tuning, and flatness. It restores causality and avoids the philosophical nightmare of uncaused creation. But it creates its own problem with the second law of thermodynamics. How do cycles reset entropy? How does a collapsing universe bounce instead of hitting a singularity? These are open questions, and until we can answer them, the cyclic universe remains a tantalizing possibility, but not a proven reality. It's a hypothesis that makes sense in some ways and breaks down in others, much like every model of the universe's ultimate origin and fate. The truth is, we're still groping in the dark, trying to understand something that might be fundamentally beyond our current framework for comprehending reality. The Big Bang might not have been the beginning, but if it wasn't, what was? And if cycles are real, how do they work? These questions sit at the absolute edge of human knowledge, where physics meets philosophy, and certainty gives way to profound mystery. If the cyclic universe hypothesis is true, if our Big Bang was just the latest iteration in an infinite series, then you'd expect there to be evidence, traces, scars, something left behind from previous cycles that we could detect if we knew where to look. And, according to some physicists, we might have already found it. The evidence is hiding in plain sight, encoded in the oldest light in the universe, and it suggests something absolutely staggering. We might not be the first universe. We might not even be the second or the 1,000th. We could be living in the ruins of countless previous cosmos, completely unaware that we're standing on ancient ground. The most promising place to look for evidence of previous universes is the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, radiation that has been traveling through space for 13.8 billion years, ever since the universe cooled enough for light to travel freely. It's the oldest light we can observe, a snapshot of what the universe looked like when it was only 380,000 years old. The CMB is incredibly uniform, almost perfectly smooth in all directions, with a temperature of about 2.7 Kelvin. This uniformity is exactly what we'd expect from the Eye's Big Bang. The early universe was hot and dense and remarkably homogeneous, and the CMB reflects that. But here's the thing. The CMB isn't perfectly uniform. There are tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations are the seeds that eventually grew into galaxies and galaxy clusters, regions that were slightly denser than average and collapsed under their own gravity. We understand these fluctuations. They match our predictions. But there are also anomalies in the CMB, features that shouldn't be there, and they've been bothering cosmologists for decades. One of the most famous is the cold spot, a region about 5 degrees across that's significantly colder than the surrounding area. It's too large and too cold to be easily explained by our standard models. Then there are unexpected alignments, patterns in the fluctuations that seem to be correlated across enormous distances in ways that don't make sense. These are sometimes called the axis of evil, because they align along a particular direction in space, which shouldn't happen in a universe that's supposed to be isotropic, the same in all directions. Most cosmologists treat these anomalies as statistical flukes, quirks in the data, or limitations of our instruments. But Roger Penrose, the Nobel Prize winning physicist, has a different interpretation. He claims these anomalies are Hawking points, scars left by supermassive black holes from the previous universe. Penrose's argument goes like this. In the final stages of the previous universe, long after all the stars have died and the galaxies have evaporated, the only significant objects left would be black holes. Over unimaginably long timescales, these black holes would slowly evaporate through a process called Hawking radiation, losing mass and energy until they finally disappear in a final burst. Now, supermassive black holes, the kind at the centers of galaxies with masses of millions or billions of suns, would be the last to go. They'd take something like 10 to the 100 years to fully evaporate, an incomprehensible stretch of time. But eventually, they would. When a supermassive black hole finally evaporates, it releases an enormous amount of energy in its final moments. Penrose argues that this energy wouldn't just dissipate. It would leave an imprint, a signature in the structure of space-time. And when the universe transitions from the infinite future of one cycle to the Big Bang of the next, through the conformal rescaling that Penrose's model proposes, these energy signatures would carry over. They'd appear in the CMB of the new universe as circular patterns, concentric rings of temperature variation centered on the points where supermassive black holes evaporated in the previous cycle. Hawking points, fossils from a dead universe. Penrose and his colleagues claim to have found these patterns. They've analyzed the CMB data and identified what they say are statistically significant concentric circles, far more than you'd expect from random chance. These circles, according to Penrose, are direct evidence that our universe is not the first. They're archaeological remnants, the last traces of black holes that existed trillions upon trillions of years before our Big Bang. If he's right, we're literally looking at the ghosts of a previous cosmos every time we study the CMB. The implications are staggering. It would mean the cyclic universe isn't just a theoretical possibility. It's real. It happened. And we have the evidence. But, and this is a massive but, most cosmologists are deeply skeptical of Penrose's claims. Multiple groups have analyzed the same CMB data and argue that the patterns Penrose identifies are nothing more than statistical noise. When you have a large data set, you can always find patterns if you look hard enough. It's a version of the Texas sharpshooter fallacy, where you fire a bunch of bullets at a barn and then draw a target around the cluster of holes afterward. Critics say Penrose is seeing patterns because he's looking for patterns, not because the patterns are genuinely significant. They've run simulations showing that random temperature fluctuations in the CMB would naturally produce circular features at the same rate Penrose observes. In other words, what he's seeing might be confirmation bias, finding what he expects to find in noise that doesn't actually contain a signal. The debate is ongoing. Penrose has responded to the criticisms, refining his analysis and arguing that the patterns are real and significant. Other cosmologists remain unconvinced. But here's what's important. Even if Penrose is wrong about the specific patterns, even if the Hawking points turn out to be statistical artifacts, the fact that this debate is happening at all is remarkable. We're at a point in physics where serious scientists are seriously discussing the possibility that we might be able to detect evidence of a universe that existed before the Big Bang. We're looking for it. We're analyzing data. This isn't philosophy anymore. It's observational cosmology. And whether Penrose's specific claims hold up or not, the door is now open. If cyclic universes are real, there should be evidence, and we might be on the verge of finding it. Beyond the CMB anomalies, there's another deep problem in physics that cyclic models might solve, and it's called the black hole information paradox. When matter falls into a black hole, it seems to disappear from the universe. All the information about that matter, its quantum state, its history, everything, appears to be lost. But quantum mechanics is very clear on this point. Information cannot be destroyed. It can be scrambled, it can be hidden, it can be spread out, but it cannot simply vanish. The laws of quantum mechanics are time reversible, meaning if you know the final state of a system, you should be able to work backward and figure out the initial state. Information is conserved, always. The problem is, black holes seem to violate this. As a black hole evaporates via Hawking radiation, it emits essentially random thermal radiation that contains no information about what fell in. Once the black hole is gone, that information is gone too, or so it seems. This is a direct contradiction between general relativity, which says black holes destroy information, and quantum mechanics, which says information must be conserved. Physicists have been arguing about this for decades. Stephen Hawking famously claimed that information is lost, and later conceded he was wrong after losing a bet to fellow physicist John Preskill. The current consensus is that information must somehow be preserved, perhaps encoded in subtle correlations in the Hawking radiation. But we don't fully understand the mechanism. Cyclic models offer an elegant solution to this paradox. If the universe undergoes cycles, if the Big Crunch or conformal transition leads to a new Big Bang, then the information that falls into black holes doesn't get destroyed. It gets transferred to the next cycle. The collapse of the universe at the end of one cycle acts as a kind of cosmic reset button, preserving the quantum information and allowing it to re-emerge in the structure of the next universe. The information isn't lost, it's recycled. The next Big Bang would contain, in some scrambled and degraded form, all the information from the previous universe's black holes. It's still there, just encoded in the initial conditions of the new cycle. This is speculative, of course. We don't have a detailed mechanism for how this information transfer would work. But it's a compelling idea because it resolves a major paradox by connecting it to another major question about the universe's origin. Two problems, one solution. Cyclic cosmology doesn't just explain why the Big Bang had low entropy, or why the universe is flat. It also preserves the fundamental principle of information conservation that quantum mechanics demands. The black hole information doesn't disappear. It escapes into the next universe. Central to Penrose's conformal cyclic cosmology is a deeply strange idea about time and the structure of the universe. Penrose argues that the infinite future of one universe, the heat-death scenario where everything has decayed and expanded forever, is mathematically identical to the Big Bang of the next universe. Let me try to explain this. In the far future, after all stars have died and all black holes have evaporated, the universe will be filled with nothing but photons and a few stray particles, all spread out over unimaginably vast distances. In this state, there are no massive particles left. Everything is massless radiation. Time becomes meaningless because there are no clocks, no processes, no change. The universe is in a sense timeless. Penrose points out that the very early universe, in the first moments after the Big Bang, was also filled with massless radiation. No atoms, yet no massive particles, just photons and energy in a hot, dense state. Mathematically, through a technique called conformal rescaling, You can transform the infinite future of one universe into the finite Big Bang of the next. The end and the beginning are the same thing, just viewed from different perspectives. It's as if time loops around, infinity becomes zero, and the cycle starts again. The universe doesn't so much bounce as smoothly transition from one eon to the next. This is extraordinarily abstract and difficult to wrap your head around, and I'll be honest, most physicists find it bizarre and unconvincing. But Penrose isn't some crank. He's one of the most respected mathematical physicists alive. His ideas about black holes and general relativity helped earn him a Nobel Prize. So when he proposes something this strange, people take it seriously, even if they don't necessarily believe it. The conformal structure argument is an attempt to solve the entropy problem and the bounce problem simultaneously, by redefining what we mean by the end and the beginning. If the transition is smooth and conformal, maybe there's no entropy crisis. Maybe the universe doesn't need to bounce in the traditional sense. It just seamlessly transitions from eon to eon. But this brings us to one of the biggest problems with any cyclic model: the bounce. How does a collapsing universe avoid becoming a singularity and instead bounce into a new expansion? According to general relativity, a collapsing universe should contract to a point of infinite density and infinite curvature, a singularity where the laws of physics break down completely. This is the same problem we have with the Big Bang singularity, just in reverse. Classical physics can't describe what happens at a singularity. The equations give infinities. Everything fails. So, how does the universe pass through this bottleneck and come out the other side as a new Big Bang? The answer, if there is one, must involve quantum gravity, physics that combines general relativity with quantum mechanics. We don't have a complete theory of quantum gravity yet. String theory and loop quantum gravity are leading candidates, but neither is fully developed or tested. Some models propose that quantum effects prevent the formation of a true singularity, creating a kind of quantum bounce where the universe reaches a minimum size and then rebounds. In loop quantum cosmology, for instance, the extreme densities of a collapsing universe trigger quantum repulsive forces that halt the collapse and reverse it into an expansion. It's not a singularity. It's a bounce, a turnaround point where quantum effects dominate. Paul Steinhardt's ekpyrotic model takes a different approach. Instead of a single universe collapsing and bouncing, he proposes that our universe exists on a three-dimensional brane, a membrane, floating in a higher dimensional space. There's another brane nearby, another universe, and periodically these branes collide. The collision releases enormous energy, triggering what looks like a Big Bang in both universes. The Big Bang isn't the beginning of time. It's the moment of collision between branes. After the collision, the branes separate, the universes expand, evolve, and eventually they collide again. The cycle repeats. In this model, there's no singularity to worry about because the universes never collapse to a point. They just collide, bounce apart, and collide again. These are fascinating ideas, but none of them are proven. We don't have observational evidence for quantum bounces or colliding branes. We barely have any observational evidence for extra dimensions, which the ekpyrotic model requires. These are speculative solutions to a speculative problem. The bounce is the Achilles heel of cyclic cosmology. Until we have a working theory of quantum gravity that can describe what happens at extreme densities, we're just guessing. One important aspect of cyclic models is that the cycles aren't identical. they're not perfect replays of the same universe over and over. Each cycle is slightly different. Quantum fluctuations during the bounce, variations in how matter and energy are distributed, different configurations of black holes. All of these factors mean that each new universe would have slightly different properties. The physical constants might vary a bit. The amount of matter versus dark energy might differ. The large-scale structure, the arrangement of galaxies, would certainly be unique. In a sense, each cycle is a variation on a theme, not an exact copy. This has interesting implications for the fine-tuning problem. We don't need to be in the only universe, or even a randomly selected universe. We're in one of the infinite cycles, and we naturally find ourselves in a cycle where the constants happen to allow for complex structures and life. We couldn't exist in the cycles where gravity is too strong or the cosmological constant is too large. Those cycles are sterile. We're here because this particular iteration of the universe had the right conditions. It's not luck, it's selection. Over infinite cycles with varying properties, life-friendly universes will inevitably arise, and we're necessarily in one of them. This connects to an even broader idea. If cyclic universes are real, there might not be just one cycling universe. There could be an infinite number of them, all cycling independently at different stages. Some in the expansion phase, some collapsing, some just after a bounce. Our Big Bang might be just one of countless Big Bangs happening throughout a higher dimensional space. In the ekpyrotic model, there could be many brains, many collisions, many cycles all happening simultaneously. We're not in the universe. We're in a universe, one of an incomprehensible number, all undergoing their own cycles of birth and death and rebirth. This is where cyclic cosmology overlaps with multiverse theory. The multiverse, in its various forms, proposes that our observable universe is just one of many. In the eternal inflation model, the quantum fluctuations during inflation create bubble universes, each with potentially different physical laws. In the many worlds interpretation of quantum mechanics, every quantum event spawns parallel realities. And now, in cyclic models, we have the possibility of infinite sequential universes in one timeline, and potentially infinite parallel cycling universes in a higher dimensional space. The cosmological landscape becomes unimaginably vast. We're not special. We're not even close to unique. We're one iteration of one universe in one cycle among infinite possibilities. So, how many cycles have there been? If each cycle lasts about 100 trillion years, from Big Bang through the Stelliferous era, the Degenerate era, the Black Hole era, to Heat Death or Big Crunch, and the process has been running forever, how many cycles have elapsed before ours? The answer is there is no answer. Infinity. You can't count to infinity. There was no first universe, so there's no way to number them. We could be universe number 10 to the 500, or 10 to the 10 to the 10 to the 1,000. The number is meaningless, because there was never a beginning. It's turtles all the way down. No matter how far back you go, there's always another cycle before that, always another universe that came before. This is profoundly disorienting. We like to think of ourselves as living in a universe with a history, a timeline we can trace backward to a definite starting point. But if cyclic models are correct, that starting point is an illusion. There is no Genesis moment. There's just an eternal process, and we're somewhere in the middle of it, with no idea where we are in the sequence. It's like being in an infinite line of dominoes falling. You can see the dominoes before you and after you, but you can never reach the first one because it doesn't exist. The line extends infinitely in both directions. That's the cyclic universe. No beginning, no end, just endless iterations, each one slightly different, each one temporary, each one eventually giving way to the next. If cyclic models are correct, if the universe truly does undergo endless cycles of death and rebirth, then there's a haunting possibility we need to consider. Information from previous universes might survive into ours. Not intact, not in any recognizable form, but present nonetheless. Scrambled, degraded, encoded in ways we barely understand, but there. We might be living in a universe that contains ghostly echoes of everything that came before. Every star that ever burned in the previous cycle, every galaxy that ever formed, every civilization that ever looked up at their sky and wondered if they were alone. All of it might have left traces in the fabric of space-time, faint impressions that carried over into our universe. And here's the truly unsettling part. If information from previous universes survived into ours, then information from our universe will survive into the next. Traces of us, of humanity, of Earth, of everything we've ever done or thought or built, might persist through the transition. Degraded beyond recognition, certainly, but present. We're not truly mortal. Not in the absolute sense. Echoes of us might reverberate through infinite future cycles, long after our sun has died and our galaxy has evaporated and our universe has come to an end. So, what kind of information could actually survive the transition from one universe to the next? Certainly not complex structures. Atoms, molecules, stars, planets, all of that gets destroyed in the final stages of a cycle. If the universe collapses into a big crunch, everything gets crushed into a singularity or near singularity where matter as we know it ceases to exist. If the universe expands forever into heat death, everything decays over unimaginable timescales until nothing remains but isolated particles separated by cosmic distances. Either way, the stuff of our universe, the tangible matter and structure, doesn't make it through. But information is more fundamental than matter. Information is abstract, mathematical, encoded in states and patterns rather than objects. And there are several ways information might persist. Quantum information is one possibility. The quantum states of particles, their entanglements, their correlations. These might leave signatures that survive the reset. In quantum mechanics, information is never truly lost, even if it becomes scrambled and inaccessible. If the transition from one cycle to the next preserves quantum coherence in some form, even partially, then the quantum information from the previous universe could leak into the next. It wouldn't be readable in any straightforward way. You couldn't extract blueprints for alien technology or messages from previous civilizations. But the information would be there, encoded in the correlations between particles in the early moments of the new Big Bang. Gravitational wave patterns are another candidate. Gravitational waves are ripples in space-time itself, and they propagate independently of matter. In the final stages of a universe, when matter has mostly decayed, gravitational waves from ancient cataclysms, colliding black holes, collapsing structures, would still be propagating through space. If the transition to a new cycle preserves some aspects of spacetime's geometry, these gravitational wave patterns might carry over. The new universe would inherit a background hum of gravitational radiation, a fossil record of violent events from the previous eon. We might even be able to detect this if we build sensitive enough gravitational wave detectors. a persistent background signal with features that don't match anything from our universe's history. Topological defects in space-time are another intriguing possibility. These are features that form when the universe undergoes phase transitions, kind of like cracks in ice when water freezes. Cosmic strings, domain walls, magnetic monopoles. These are all theoretical structures that might form in the early universe. If the transition between cycles involves a phase transition of some kind, the topological structure of spacetime might preserve certain features from the previous cycle. These defects would act like scars, imperfections in the fabric of space that carry information about how the previous universe ended. The large-scale distribution of matter and energy is perhaps the most plausible way information could leak through. Even if individual particles are destroyed, the overall pattern, the density fluctuations, the regions of slightly higher or lower energy, these might influence how the next cycle begins. The Big Bang of the new universe wouldn't be perfectly smooth and random. It would be seeded by structures inherited from the collapse of the old universe. We see hints of this in our own universe. The CMB isn't perfectly uniform. There are fluctuations, patterns, structures that seem almost too organized to be purely random. Could some of these patterns be inherited from a previous cycle? In Penrose's conformal cyclic cosmology, information transfer is built into the model. Penrose argues that massless particles like photons and gravitons at the end of one universe are mathematically equivalent to massless particles at the beginning of the next. In the far future, when all matter has decayed and only radiation remains, the universe is filled with photons, traveling through an ever-expanding void. Through conformal rescaling, this infinite expansion can be mapped onto the dense, radiation-filled state of a new Big Bang. The photons from the end of one eon become the photons at the start of the next. Their information content, the patterns in their distribution and energy, persists through the conformal boundary. This means the CMB we observe today, the oldest light in our universe, might contain encoded data from the final moments of the previous universe. Not just the afterglow of our Big Bang, but also a fossil record of the universe that came before. If Penrose is right, we're not just looking at our own past when we study the CMB. We're looking at someone else's ending. The ekpyrotic model offers a different mechanism for information transfer. In this scenario, our universe exists on a three-dimensional brain floating in a higher dimensional space, and there's another brain, another universe nearby. Periodically, these brains collide. The collision releases enormous energy, triggering what looks like a Big Bang in both universes. During the collision, the brains don't just bounce off each other elastically, they interact. Gravitational effects, vibrations in the brains, ripples in the higher dimensional space, all of these can transfer information from one brain to the other. Our universe's properties, the strength of gravity, the amount of dark matter, the distribution of galaxies would be partly determined by the state of the colliding brain. We'd inherit information from the sister universe at the moment of collision. And when the brains collide again in the next cycle, information from our universe would transfer to the next iteration. This leads to a speculative but absolutely fascinating question. Could an advanced civilization in a previous cycle deliberately encode information to survive the transition? Imagine a civilization billions of years more advanced than us, aware that their universe is approaching its end. They know about the cyclic nature of the cosmos. They understand the physics of the bounce or the conformal transition. Could they engineer a message designed to persist? They couldn't send physical artifacts, obviously. But they might be able to create specific patterns in gravitational waves, manipulate the distribution of supermassive black holes, or engineer quantum states designed to be stable through the reset. They might encode information in the large-scale structure of spacetime itself, in the topology, the curvature, the symmetries. A message not written in words or symbols, but in the fundamental properties of the universe. Would we recognize such a message if we found it? Probably not, at least not initially. It would look like a physical law or a cosmological parameter or an anomaly in the data. We'd measure it, study it, try to explain it with natural processes. Only if we looked very carefully, if we noticed patterns that seemed too specific, too organized, too improbable to arise by chance, might we suspect we were looking at something deliberately created. It's the ultimate SETI problem. Searching for signals not in radio waves from nearby stars, but in the structure of the universe itself, in phenomena that predate the Big Bang. The message wouldn't say hello in any language we'd understand. It would be encoded in mathematics, in the relationships between physical constants, in patterns that violate our expectation of randomness. Finding it would require not just sensitive instruments, but a radical shift in how we think about what counts as evidence of intelligence. If information leaks between cycles, there's another profound implication. Successful universes, ones that produce complex structure, stars, galaxies, planets, life, might be more likely to produce similar conditions in the next cycle. There'd be a feedback loop. A life-friendly universe would influence the initial conditions of its successor in ways that make the successor more likely to also be life-friendly. Over many cycles, the universe would optimize itself for complexity and structure. Not through design, not through intention, but through a kind of cosmic natural selection. Cycles that produce interesting outcomes leave stronger traces, more organized information, which seeds the next cycle with better starting conditions. Sterile cycles, ones that fail to produce galaxies or stars, would leave minimal information and be less likely to spawn interesting successors. This is a cosmological version of the anthropic principle. We exist in a life-friendly universe, not because we got lucky, but because we're the product of countless previous cycles that gradually tuned the conditions toward life-friendliness. The fine-tuning of physical constants, the low entropy of the Big Bang, the flatness of space, all of these might be the result of optimization over infinite iterations. We might owe our existence to a vast cosmic selection process that's been running since, well, forever. Each cycle slightly different, each one leaving information that influences the next, and, over time, the cycles that work persist and propagate while the ones that don't fade away. It's evolution applied not to organisms, but to universes. So how could we actually test this? How could we detect information from previous universes? There are several approaches, and remarkably, we're starting to have the technology to try them. First, look for non-random patterns in the CMB that go beyond what standard inflation theory predicts. We've already discussed Penrose's Hawking points, the concentric circles that might be evidence of evaporating black holes from the previous eon. Whether those specific claims hold up or not, the broader search is valid. If there are patterns in the CMB that we can't explain with processes from our universe alone, that's a red flag. It could be noise, or it could be a signal from something older than the Big Bang. Second, look for violations of expected entropy distributions. entropy should be smoothly increasing from the Big Bang onward. If we find regions or scales where entropy doesn't behave as expected, where there's more order than there should be, that could indicate inherited structure from a previous cycle. The universe shouldn't have certain types of organization unless something seeded it. If we find those seeds, we need to ask where they came from. Third, search for quantum entanglement anomalies. Quantum entanglement is usually local, involving particles that interacted in the past. But if information from a previous universe leaked into ours at the quantum level, we might find entanglement patterns that don't have a causal origin in our universe's history. Particles that are entangled despite never having been in contact, or entanglement structures that suggest connections to systems outside our observable universe. This is highly speculative, and we don't yet have the technology to test it, but it's a place to look. Fourth, analyze the gravitational wave background. We've only recently started detecting gravitational waves from merging black holes and neutron stars. But there should also be a stochastic background, a constant hum of gravitational radiation from countless sources throughout cosmic history. If that background has unexpected features, patterns that don't match what we'd predict from known sources in our universe, it could be fossil radiation from events that occurred before the Big Bang. We're building more sensitive detectors: LIGO, LISA, future space-based interferometers. As these come online, we'll be able to map the gravitational wave background with increasing precision. And we might find something strange. But even as we discuss these tests, there's a philosophical weight to the idea of information leaking between universes that's almost overwhelming. If information persists, then, in some sense, previous universes aren't truly gone. They ended, yes. Their stars died, their galaxies evaporated, their civilizations perished if any existed. But they left traces. Everything that happened in them, every event, every life, every thought, left an imprint in spacetime's structure. The universe has a memory. Not a conscious memory, not the kind we experience, but a physical record encoded in its fundamental properties. Previous universes are fossils embedded in the substrate of reality. And if our universe leaves traces, then we're part of that fossil record. Humanity, Earth, the Sun, the Milky Way, everything we are and everything we've done will be encoded in the structure of the next cycle. Degraded, unrecognizable, scrambled beyond any hope of reconstruction, but present. In a strange way, this is a form of immortality. Not the kind any individual would want, not the kind that preserves identity or experience or consciousness, but our information will persist. Long after the sun expands into a red giant and engulfs the Earth, long after the Milky Way collides with Andromeda, long after the last star in the universe burns out and even the black holes evaporate, echoes of us will remain. In the quantum correlations of the next universe, in the gravitational wave background, in the topological structure of space-time. Future cosmologists in the next cycle, if they exist, might look at the CMB of their universe and see faint patterns that carry information about ours. They won't know what they're looking at. They won't be able to decode it or understand it, but will be there in the data, a ghostly presence from a universe that died trillions of years before they were born. There's also a question about cumulative information. If information leaks from one cycle to the next, does it accumulate? Does the universe get more complex over time, carrying more and more data from previous iterations? Or is there a maximum information capacity, a limit to how much can be stored in the fabric of space-time? The math here gets speculative, but some models suggest that information might follow thermodynamic rules. It can increase in certain senses, becoming more scrambled and spread out, but there might be resets during the bounce or the conformal transition that prevent infinite accumulation. Information from many previous cycles might be compressed or overwritten, with only the most recent or most stable patterns surviving in detectable form. Alternatively, the universe might develop a kind of evolutionary history, a layered record where information from different eras is stacked on top of each other. The oldest information, from cycles thousands or millions of iterations ago, would be the most degraded and hardest to detect. But it would still be there, buried deep in the structure of the universe like geological strata. We'd be living in a cosmos with an unimaginably deep history, most of it inaccessible to us, but theoretically recoverable with the right instruments and the right theories. It's like archaeology, but instead of digging through dirt to find ancient civilizations, we're analyzing the fundamental properties of space-time to find traces of previous universes. Cosmic archaeology. And we've barely started scratching the surface. Step back for a moment and try to imagine the full picture. Not one big bang, but an infinite sequence of them stretching backward and forward through eternity. Each universe a single frame in an endless film. Our universe, with its 13.8 billion year history, its hundreds of billions of galaxies, its countless stars and planets, all of human civilization from the first stone tools to space telescopes, all of it is just one frame. We see it as static, as complete, as the universe, the totality of existence. But it's actually a fleeting moment in an eternal process we can barely begin to perceive. Before our frame, infinite frames. After our frame, infinite frames. Each one slightly different, each one temporary, each one just as real as ours while it lasts. We're not watching the film, we are the film. Or rather, we're a few pixels in one frame of a film that never ends. At this scale, time becomes almost meaningless. If the cycles are truly infinite, where are we in the sequence? What number universe is this? The question has no answer because there's no start to count from. There was never a first universe, so there's no way to number them. You could say we're in universe number 10 to the 500, but that number is completely arbitrary. We might as well say universe number 7 trillion, or universe number Googleplex. It doesn't matter. Every cycle is equally real and equally temporary. None of them are special. None of them are the original. The entire 13.8 billion year history of our universe, from the Big Bang to now to the eventual heat death trillions of years in the future, that's just one frame. Our galaxy's 13 billion year existence, a small cluster of pixels in that frame. The sun's 10 billion year lifespan, a handful of pixels. Earth's 4.5 billion years, even less. The 200,000 years that modern humans have existed. You'd need a microscope to see it in the cosmic frame. Your life, my life, all of human history, the rise and fall of empires. Every war ever fought, every book ever written, every person who ever lived, it's barely visible. A few sub-pixels in one frame of an infinite film. And yet, from our perspective, it's everything. It's all we know. It's all we can see. There's an analogy that might help. Imagine a goldfish born in a bowl. That goldfish, assuming it has some capacity for thought, would naturally assume the bowl is the entire universe. The water, the glass walls, maybe a plastic castle and some colorful gravel, that's the totality of existence as far as the goldfish is concerned. It has no concept of the room the bowl sits in, no concept of the house that contains the room, or the street outside the house, or the city, or the planet. The bowl is everything. That's us. We observe our universe, we measure it, we study it in exquisite detail, and we naturally assume it's everything. But we might be just one bowl in an infinite house of aquariums. Each bowl going through the same cycle, expansion and contraction, birth and death, completely unaware of the others. Some bowls in early expansion, some approaching their end, some in the middle of their lifespan like ours. All of them isolated, all of them thinking they're the only universe, all of them wrong. The frustrating thing is we can't see the pattern. We're trapped inside our frame. We're like characters in a movie trying to understand the projector. We can analyze our frame in incredible detail. We can measure the cosmic microwave background to exquisite precision, map every galaxy, understand the physics of stars and black holes, trace the history of our universe back to fractions of a second after the Big Bang. But we can't see the frames before or after. We can't step outside and look at the full film. The evidence for previous cycles, if it exists, is encoded in our frame. The CMB anomalies, the fine-tuning of physical constants, the mysteriously low entropy of the Big Bang, these are clues, fingerprints left behind by previous universes. But we can only infer what they mean. We can't replay the previous cycle. We can't fast forward to see what comes next. We're stuck here, in this moment, trying to reconstruct an infinite history from fragmentary evidence embedded in the structure of space-time. It's like doing archaeology without being able to dig, only able to analyze the surface, knowing there are layers upon layers beneath, but unable to access them directly. What's the fate of our universe in these cyclic models? Eventually, and by eventually I mean trillions of years from now, our universe will either collapse into a big crunch or expand forever into heat death. Which one depends on the balance between gravity and dark energy. Right now, dark energy is winning. The expansion of the universe is accelerating, not slowing down. If that continues, and we have no reason to think it won't, the universe will expand forever. Galaxies will drift beyond each other's cosmic horizons. Stars will burn out. Black holes will evaporate. Eventually, the universe becomes a cold, dark, nearly empty void with isolated particles separated by unimaginable distances. Heat death. Maximum entropy. Nothing happens anymore because there's no energy left to make anything happen. But in some cyclic models, particularly Penrose's conformal cyclic cosmology, heat death isn't the end. It's the beginning of the next cycle. The infinite future of one universe, when stretched to its limit, becomes mathematically equivalent to the Big Bang of the next. Time doesn't end. It resets. The universe smoothly transitions from eon to eon. Alternatively, if dark energy somehow reverses, or if there are mechanisms we don't understand, the expansion could slow and reverse. The universe would begin contracting. Galaxies would collide more frequently. The cosmic microwave background would get hotter instead of cooler. Eventually, everything collapses back toward a singular state, a big crunch which might bounce into a new Big Bang. Either way, our universe is temporary. This configuration, this particular arrangement of matter and energy and physical laws, will not last forever. It's a phase, a moment, a frame. What happens to us when the universe ends? If it's a big crunch scenario, we don't make it anywhere near the end. Life will be gone long before the final collapse. The sun will exhaust its hydrogen fuel in about 5 billion years, expand into a red giant, and likely engulf Earth. even if humans somehow escape to other star systems, all stars eventually die. In a few trillion years, the last stars will burn out. No more energy sources for biological or technological civilizations. In the final stages of a collapse, as the universe contracts and heats up, any remaining structures, planets, atoms, even subatomic particles, would be ripped apart by extreme temperatures and densities. Everything gets destroyed well before the singularity. If it's a heat-death scenario leading to a conformal reset, the process is slower but no less final. We fade away as the universe goes dark. The stars burn out. The energy sources disappear. Civilizations, if any remain, would have to become increasingly efficient, rationing the last dregs of available energy until finally there's nothing left to sustain complexity. And then we're gone. But information about our existence, as we discussed earlier, becomes a faint whisper in the structure of the next cycle. We don't survive as conscious beings, but as patterns, as correlations, as subtle influences on the initial conditions of the next universe. A ghost in the machine. Could life exist in every cycle? That's an open question. If physical constants vary slightly from cycle to cycle, most universes might be sterile. No chemistry, no stars, no planets, nothing that could support life as we know it. Change the strength of the electromagnetic force even slightly, and atoms don't form. Change the mass of the proton, and you can't get stable nuclei. Change the cosmological constant too much, and the universe either collapses immediately or expands so fast that no structures form. The space of possible universes is vast, and the space of life-friendly universes might be vanishingly small. We might be in one of the rare cycles where the constants happened to align just right. But there's another possibility. If information leaks between cycles, if successful universes influence their successors, then there might be a feedback mechanism that ensures most or even all cycles are life-friendly. The universe optimizes itself over time, not randomly trying every possible configuration, but building on what worked before. In that case, life might be common, even inevitable, across cycles. We don't know. But if cycles are truly infinite, then every possible configuration of physical laws will occur eventually. There will be cycles with no stars. Cycles where gravity is too weak and nothing ever collapses into galaxies. Cycles where the strong nuclear force is too strong and all hydrogen fuses immediately into heavier elements. And cycles like ours, where everything is just right. Across infinity, every possibility is realized. Somewhere, somewhen, in some cycle, every conceivable universe exists. This brings us to a deeply disturbing idea that the philosopher Nietzsche called eternal return. If cycles repeat infinitely with slight variations, eventually, not just eventually but inevitably, a configuration identical or nearly identical to ours will recur. The same arrangement of particles, the same galaxies, the same stars, the same planets. Another Earth, another Sun, another Milky Way. Another you reading this exact script. Not a copy, not a simulation. The original you, reconstituted in a future cycle so far away that the time elapsed since our universe is unimaginably vast. But it will happen. Given infinite time, any configuration with non-zero probability must occur. And this configuration, our universe, demonstrably has non-zero probability because it exists now. So it will exist again, and again, and again. The same atoms, the same chemical reactions, the same neurons firing in the same patterns, the same choices, the same thoughts, the same experiences. Everything that has happened will happen again. Your birth, your life, your death, all of it will repeat infinite times. Not because of fate or destiny, but because of statistics. Infinity is long enough for everything to happen, including exact replays. Nietzsche found this idea horrifying. He called it the heaviest weight, the most extreme burden that could be placed on a person. To know that your life will recur infinitely, with no variation, no escape, no ability to change anything. But there's another way to think about it. If your life recurs infinite times, then you are, in a sense, immortal. Not in the sense of living forever in one timeline, but in the sense of existing across infinite timelines, infinite cycles. You die in this universe, but you're reborn in the next iteration of this exact configuration. And because you have no memory of previous cycles, each one feels like the first. From your subjective experience, this is the only time. You're not aware of the infinite replays. So, does it matter? Philosophically, eternally recurring existence is strange and unsettling, but practically, it's indistinguishable from a single finite existence. You live, you die, the cycle continues, and eventually you live again. So why might the cyclic universe be correct? Let's summarize the evidence and the arguments. The CMB anomalies, particularly the patterns that Penrose identifies as Hawking points, suggest structures that predate the Big Bang. The fine-tuning problem, the fact that physical constants seem exquisitely calibrated for life, is naturally explained if universes undergo cycles with slight variations, and we find ourselves in a life-friendly iteration. The low-entropy mystery, the fact that the Big Bang started in such an improbably ordered state, makes sense if the ending of one cycle naturally produces the beginning of the next. The flatness problem, the fact that the universe is spatially flat to extreme precision, is solved if flatness is an attractor state that emerges over multiple cycles. The black hole information paradox, the apparent destruction of information when black holes evaporate, is resolved if the information transfers to the next cycle. A cyclic universe elegantly solves multiple problems that plague standard Big Bang cosmology. It's not proven, not even close, but it's increasingly difficult to dismiss as pure speculation. The problems it addresses are real. The solutions it proposes are plausible, given exotic but not impossible physics. But why might it be wrong? The entropy problem remains unsolved. We don't have a convincing mechanism for resetting entropy between cycles. The second law of thermodynamics is ironclad, and any cyclic model has to explain how entropy doesn't accumulate to maximum across infinite cycles. We don't have a mechanism for the bounce. Classical general relativity predicts a singularity, and we don't yet have a proven theory of quantum gravity to describe what happens at those extreme conditions. Dark energy is currently accelerating the expansion of the universe, and we see no sign of it weakening or reversing, which makes a big crunch scenario unlikely. The evidence in the CMB might be statistical noise. Penrose's patterns might be the result of confirmation bias, finding what you expect to find in data that's inherently noisy. And then there's Occam's razor, the principle that simpler explanations are generally better. Standard Big Bang cosmology, for all its problems, requires one universe with one beginning. Cyclic cosmology requires infinite universes across infinite time, with exotic physics at the transitions. Why add all that complexity if a simpler model works? The counter-argument is that the simpler model doesn't fully work. It leaves too many questions unanswered. But the debate is far from settled. The existential weight of the cyclic universe is profound. If this is true, nothing is permanent. Not just our lives, which we already know are temporary, but our universe, our physics, our history. Everything is fleeting on a cosmic scale. The stars will die. The galaxies will disperse. The laws of physics that govern our universe might be different in the next cycle. Nothing lasts, but at the same time, nothing is truly lost. Information persists. Our universe is part of an eternal process. We're not the end product of creation, the final goal of some cosmic plan. We're one iteration in an endless experiment. The universe trying different configurations, exploring different possibilities, not with intent or purpose, but simply because that's what happens when you have infinite time. We're one frame in a film that never ends. And when our frame is over, the film continues. New frames, new universes, new possibilities. The process doesn't stop. It can't stop. There's no off switch for eternity. Look at the night sky tonight. Those stars, that moon, the darkness between them, it's all temporary. In a few billion years, the stars you see will be gone. In trillions of years, all stars will be gone. The universe will go dark. But it's also eternal. This exact configuration, this exact arrangement of matter and energy might have happened before in a previous cycle. It might happen again in a future one. You might have stood here before, looking up at the same sky, thinking the same thoughts without any memory of it. And you might stand here again, infinite times, each one feeling like the first. The universe might be much stranger, much older, much more vast than we ever imagined. The Big Bang wasn't the beginning. It was just the latest beginning. A reset, a reboot, a new iteration in an endless series. And when our universe ends, billions or trillions of years from now, it won't be the end either. Just another transition, another bounce, another conformal reset, another collision of brains, whatever the mechanism turns out to be. Another frame in the film, and the film keeps playing. Forever. No start, no end, just an eternal cosmic heartbeat. Expansion and contraction, birth and death and rebirth, on and on through infinite time. We're living in one heartbeat, one brief moment between the infinite past and the infinite future. And somehow, against all odds, we're here to witness it, to measure it, to try to understand it. We're one frame, but we're a frame that can think, that can observe, that can ask questions about all the other frames. That has to count for something.